Hi. In part 3, we are going to study the concept called modulo. This is an extension of the concept for remainder, for divisibility, and remainder. So recall that if you have two numbers, m and n, usually m is a larger one and it is a smaller one. If you divide divide n by m, then then you can express m as n some number and another number. This number is called some quotient, and we have the remainder. Okay, better. Yeah, quotient and a remainder. But for modulo, this is the area where sometimes all you need is a remainder. Usually you don't care about the quotient. There are several reasons why. But if you only care about the remainder, then there are better or quicker or more fun ways to study the remainder of a number. And that is called a modulo. So recall the motivation for this modulo is that think about it as clock. Usually we have 12 hours clock from 12, 1 to 3, 4, 6, 7, 5, 10, 11. So you start at 1. If you add an hour, you get 2. If you add an hour, you get 3. If you add an hour, you get 4, 5, 6, and so on. If you add 12, if you add an hour, the hand of the clock rotate back to 1. 12 plus 1 becomes 1. So in a sense, 1 and 13 is at the same spot. 1 around the clock, 1 and 13 are at the same spot. So are 2 and 14, 3 and 15, and so on. And this is what we use every day, right? At 1 p.m. is 12. There's two different ways to express term. But here's the concept. Right? Sometimes you have a clock, or you study something that happens in a cycle. It goes around a cycle and only loops through some fixed numbers. And sometimes you don't care whether it's going around the clock 2 times or 3 times. All you care about is where it finally lands on. If it start at 1 and then they move 100 hours around the clock, where it will finally be landed on. Maybe you start, you have a code, you run it at 12 p.m. and it takes 100 hours. You want to know when it will stop. So that's the idea. Sometimes all you care about is where it lands. But that means in this case, in this what we call the clock arithmetic, 1 and 13 are the same number. You don't know whether it's 1 a.m. or 1 p.m. or 13 o'clock or any of those numbers. They are the same. Because all we see is, it's the hand of the clock points to that single number. And interestingly, it's also the same as 25. If you are at 13, or in this case it's 1, and then you move around the clock another 12 hours, you will get to 25. It's like 24 hours from 1. And that's again the same. It points to the same number 1 on the clock, and there's no way to tell whether it's 25 or 1. So they are all the same, and so are other numbers. That's the concept behind the arithmetic on the clock. And the example I'm using is for 12-hour clock, but the image here are numbers. The image here has only like for this image there are only 5 numbers. The thing about this clock is usually you start at 0, not 1. Because if you usually if you want to tell time, like you use 0 a.m. as the start of the day. Like you don't start at 12 p.m. Sometimes you do. I mean 12 a.m. Sometimes some people do. But on the clock, if you have a digital clock, it starts at 0. So that's the start of the cycle. And then it goes around clockwise. It doesn't have to be in a circle. It is easier to visualize when you think of it as a circle. But even there just just 5 different numbers. Kind of loops. From 1 0 to 1 to 4 to 3 to 4 and then back to 0. 2 to 3 to 4 back to 0. And so on. So that's what we have here. A clock with 5 numbers. And on the right hand side, if you zoom in, like what each region or what each number represents, like at 0. If you look around the clock one time, 1, 2, 3, 4, 5, you will land at 5. So the number 5 and the number 0 are the same. So it's 10, 15, 20, 25, 30 and so on. There are lots of numbers on the section. And you also notice that there are some negative numbers. Because it's a clock, it's a circle, right? You are not restricted to move only counterclockwise. You are allowed to move. You are not restricted to move clockwise. You are allowed to move counterclockwise as well. If moving one step clockwise represents 1, and moving one step counterclockwise would represent -1. So that would be -1. You start at 0, and you move counterclockwise 1 section or 1 step, you get -1. And that's what you see here. Like 4 and -1 points to the same section, to the same direction. And then you can go -2, that's -2 there, and 3 part, and then -3, and a step, and then -4, and then back to 0. That's why we have -5 there. This pattern keeps repeating. You can move counterclockwise as many times as you want. That's gonna generate lots of numbers. And they all fall in one of these 5 regions. So there are lots of numbers, and those numbers they are what we consider the same. And if they're not the same, then why don't we just use some what we could call a representation. Representers. And so these 5 numbers 0, 1, 2, 3, and 4 represents its section. The 0 would represent the section on top. It represents all the numbers that are 5, 10, 15, 20, and so on. -5, -10, -15, -20, and so on. All the numbers in this section. 1 also represents -6, 11, 16, 12, 26, -4, -9, -14, -15, 19, and so on. So there's that means we don't have to know all these numbers. Like, all we need to care maybe all the compute things are these 5 numbers. And so that's why we are at if the arithmetic is done on the clock, then all we need are those 5 numbers. And hopefully things will be simpler. There are only 5 numbers, like not infinite. But that's the idea. And then we have to divide it here. So the first half, if you are given 3 numbers a, b, and n, and it's positive, and this is important, then if you have n divides a minus b, that might be a weird concept, but I'm hanging there for a moment. If n divides a minus b, for instance, if a is 10, b is 2, n could be 4. Because 4 divides 10 minus 2. This would work. These three numbers, this triple would work. And if n divides a minus b, then we say a is congruent to b mod n. A is congruent to b mod n. So these two statements mean the same thing. They are equivalent. And so that's how we define the modulo. We will see soon that this will simplify things a lot. So here a and b A is congruent to b mod n, and the congruent, the C word mean they are kind of the same. In the sense that we can use one or the other. We keep have the same result. So that's the definition. A and b represent two numbers that we don't know where it belongs to. But n, this is the important one. And this n is the number of digits around the clock. If your clock has five numbers or 5 sections, then n is 5. In this circle, n is 5. On the clock, n is 12. 12 numbers around the clock. Right, and then we say that two numbers are the same, two numbers are congruent. Right? If the difference is divisible by n, or if n divides the difference. What do you mean by that? Well, if you go back here, it is just simply ask if two numbers are on the same region. So for instance, if we ask you whether 29, and 4 are in the same section, around this 5 section clock, you will say, oh yeah, it is. It's there. They are in the same section. It's easy, right? If I give you this image, you can just, find them. But if I don't give you this image, if I ask you about, 101 and 56, are they in the same section? Right, yeah, of course, I don't recommend you, list all the numbers up to 101. That will take forever. But the way to paraphrase this question is, if you start at 36, if you rotate around the clock, or to go back to the same section again over and over and over, would it be in the same region? And we have to come back here and ask what it means for two numbers to be in the same section. If you start at 16, you would have to add 5 to get to when. Oh, sorry. You would have to add 5 to get 21. Or in other words, the difference here is 5. You can see here if two numbers are 5 units apart, or if the difference is 5, then you can. But if you start from the low one and goes around the clock, one time you will end up with the other number. If the difference is 5, and you can see if the difference is 10. If you go around the clock twice, and you move 10 steps ahead. So if the difference is 10, it means you are guaranteed to loop around 2 times and go back to the same section. And so on and so forth. So this is the idea behind the divisibility. And you can see that this is the n. This relates to n. So that means two numbers are in the same section. Let's say 27 and 23. If their difference is a multiple of n, is 5 times something. If you can go around the clock 12 times, then we say that they are in the same region. And that's why. That's how we but the definition below. To test two numbers, we take a difference. If that difference is a multiple of the number n. So yeah, let's go to some quick examples. So given an integer a and modulo n by 3 other integers that are congruent to a in that modulo. For the definition we have above is a congruent to mod n. Given 3 numbers there, but here you are asked to find b. Given a and n, and then you ask to find b. Let's satisfy that. For instance, for 2 mod 5, you want numbers that is congruent to 2 mod 5, or that 2 is congruent to that number mod 5. And so again, you can go to the definition, or you can go to the formula here, or you can go to the definition. Yeah, okay, if I'm around the clock, 5 steps, and if I'm at 2, how do I get back to 2 again? You can go back. You can move forward 5 steps. That should move you back to 2. 5 steps when you go to 7. Oh, you should do it there. If you move 5 steps, you get to 7. You move another 5 steps, you get 12. If you move another 5 steps, you get 17. And so for a, you can just simply say that b equals to 7, 12, and 17. And etc, just in case, to remind you that, there are more, but these 3 are the ones that we can find easily. What about b? 20 mod 9? You want to find, if you add 20, what are other numbers that you can find in the same section? Again, there are 1, 2, 3, 4, 5, 6, 7, 8, 9 sections. And 20 is, I think it's here. Could be wrong. Suppose that's 20. You want to get to a different number. Let's say this time we go backward, not forward. Maybe move counterclockwise. If you move clockwise, you get the next number, 7, 12, 17, and so on. You can move counterclockwise and subtract that number by the number of sections around the clock. You are at 20, you move around the clock 1 full round, so 9 steps back. So that should give you to 11. If you move 9 steps counterclockwise, you will get back to the same place. That number is 11. And of course, you can repeat. If you move that back, you get 2. You can also move back 1 more round. And that gives you 2 minus 9, which is minus 7. You go back there. And that means for b, we should not use the same as for variables and the b is not 20. 11 to 7. And here's some examples. Of course, you are free to do anything you want, but simple ones are there. And lastly, we have 11 mod 3. Oh, sorry, minus 11 mod 3. So minus 11 congruent to mod 3. For mod 3, there are only 3 sections. Let's say you are at 11. Oh, sorry, minus 11. And yeah, the negative number is more difficult to deal with, but you can, if you take some time, you can do. Okay, one full round. You add 3, you get minus 3. Oh yeah, I should say that minus. Yeah, minus 9. Okay, now back to minus 8, because minus 11 plus 3 is minus 8. Go another round, you get minus 5. If you go another round, you get minus 2. I should use different color. But yeah, anyway, for C, okay, there it is. The examples we found were b equals to minus 8, minus 5, and minus 2. 3 numbers. That's how you find its friends. That's how you find all the numbers that are in the same section. But again, from now on, we will focus. If you get any numbers, like if you want to do something with 17, since 17 and 2 are the same, they are in the same region, right? There's no difference between these two, then it is easier to use 2 to do math instead of 17. We see that for a moment. Like these are the properties of the modulo. Maybe these are bad. You don't. You can pause and read, but I think you don't have to. This is simply saying that you can add numbers together. You add numbers. You have if you have A and B that are in the same they are congruent. They are in the same class, the same part of the clock. Now, if you move both forward by k steps, then the result A plus k and B if A and B are equivalent, or if A is congruent to B mod n, then if you add k on both sides, you get the same result. Just like you have A equals B, then A plus k equals to B plus k. And that can be easily seen as, if you are at the same place and you both, if you and your friend is at the same place and you both move around the lab, around the circle by the same amount, then you both should still end up in the same place. So addition works as usual. Multiplication also works as usual. It is slightly more difficult to see. A times k is equivalent to b times k. We'll see in a moment how to apply that. Then we also have an addition, but here we add two different four numbers, two different pairs. You have a pair AB, they are the same. We have a pair CD, they are the same. If you add them up, they are still the same. And lastly, I'm missing the mod n. Again, if A and B are the same, are equivalent, C and D are, sorry, if A and C are congruent, A and B are congruent, C and D are congruent, then their products are also congruent. Again, this may be confusing why, what and why and how we use that. Let's try an example. So 22 plus 12 mod 7? Find the result. What is that congruent to? Yep, so it's B. What's that number congruent to? So for A, it is tempting to add them up first. Is it not wrong to say that, oh, the sum is 34 mod 7? Then you do the math, right? What is 34 in mod 7? I think it's about 6 mod 7. This is totally correct in terms of math. If you add two numbers, you can add them up first and then do the modulo to reduce that to a smaller number. Let me say it's a 1. That's one way. Or 2. Let's say that's a better way. Usually a better way if you have large numbers. You start saying that, okay, what is 22? What is 12? Because in sense these two are large number, at least they are larger than 7. And so maybe we can, use smaller numbers to work with. That would be better, maybe more healthy. So you can do the math and say, oh, 22, if you move back 2 steps, like for 3 steps, you get 1. The difference is 21. The other one is 7 times 3 too. They are in the same section in mod 7. Then when we're bottom 12, 12 is 5. And you move around the clock back 1 time to get 5. And then that means when you add them up, you can add their representation instead. So you can add 1 and 5 instead. I can't stop my habit of putting the parentheses around the mod. So you can add the smaller numbers instead. And because again they are the same. So why don't we use the smaller number? 1 plus 5 is of course 6. So that's and that's better in sense that if you have large numbers, if you have 3 or 4 different numbers to sum, or maybe it is easy to see for each number what is the remainder or what is the modulo. Right, then maybe you can get this easier than summing it first and then do the modulo. Okay, maybe the first example is not convincing for you. Right? Oh, why do we have to do that? Yeah, let's try B. The first way to find the product is find the product first. Let's just do the product. You get what 264 mod 7. To do the math. Okay, if you divide it by 7, get what? Get 26, 7, 21, 54, the 7, 49, 6, 5. Let me slow down a little bit. 54, 7, that's 49, that's 5 is the remainder, so 5 mod 7. Well, actually, I think I forget to say that, but yeah. If you write 264, 7 times something plus q. Oh, that's side D. Yeah, okay. Yeah, you can use the division if you express 264 as 7 times r plus q. Then 264 is congruent to q mod 7. Because they are different, you move q to the left hand side, you subtract that, you get 20 times something. And so that's what we get here. They are the same around the mod 7. If you start at q and you move around the clock r times the 7 r steps, then you get 264. And so yeah, that's one way. But you can see that involves doing computing a product and then use the long division. Maybe we don't want that. Maybe we are lazy. And here this is a good place to be lazy because here if you transform that 22, you say, oh, that's pretty large. Let's choose 1 instead. Because here 22 and 1 are the same for mod 7. Only for mod 7, not for anywhere. And what about 12? 12 is the same as 5. Maybe you should use. Yeah, that's 5. Oh, sorry. Way 2 is 21, 12 is connected to 5. So you can see, oh, that's 1 times 5, that's 5. Mod 7. And we finish that in like 5 seconds. So now it's your choice. Do you want to do the one above or down here? Do you want to multiply 2 numbers and then do a long division? Or just do some basic modulo stuff and multiply them out? Your choice. So that's example 7. Right. And okay, yeah, that's the last one, right? Yeah, before the exercise. Yeah, and this is the reason why you shouldn't do multiplication first. And so for A, in the A is you have two large numbers, you do a product. Then for B you have powers, 3 to 100. Is that gonna take forever to do? I don't recommend you do that by hand, or even use your calculator, because I'm sure it's gonna break. Let me try that. Maybe it's not gonna break. So if you try compute t to 100, evaluate. Sorry, it is too long for us to display. If you insert anyway, yeah. Yeah. Are you gonna compute that? Yeah, your choice. But suppose we don't want to. Suppose we all agree that it's a bad idea to try to compute that number in mod 8. Do we have any alternative solution? Sure. Yeah, luckily we do. But let's start from A first. A is a simpler one. So we have two numbers and they are mod 10. And as before, like the first step is to, find is equivalent, or find a smaller number that can be that can represent this large number. If you divide number by 10, then the mod or the remainder is that last digit. If you divide that by 3, the remainder is 3. If you divide that by 4, the remainder is 4. Okay, so that's what we have. That means the product is just the product of these two smaller numbers, which is nice because we get 12. Yeah, that's quick. That's a lot quicker than multiplying to get, I don't know, 4 millions. Oh, and this is correct. You can answer that it is 12 mod 10, but maybe not always, but as a rough thumb, you should also divide. You should simplify it as much as you can. 12 mod 10. If you move clockwise one step, if you subtract that by 10, move back 10 steps, you get 2. So it's a smaller and nicer number to work with. So that's A. That's how you can simplify the multiplication. But what about B? You're gonna multiply things 100 times? No, right? So the idea is we want to simplify that to something small, to something smaller. And hopefully this will be like 1 or minus 1. Where if it's 1 to the power of something, it's always 1. If it's 1 to some power, it's 1. If it's minus 1 to a power, then it's plus or minus 1, depending on the number on the top. So let's see if we can simplify that. First, can we find the relationship between 3 and 8? Maybe not, right? So if you wanted to change 3 to something else, maybe you get 12. 8. And 12 is, not a friendly number. 12 is still large. Or if you subtract that by 8, you get minus 5. You want to change that 3 to minus 5? Maybe. Maybe not, because 3 is already small. So the trick here is we, instead of doing a power of 100, maybe you can do something like 3 squared to the power of 50. Well, actually this actually involves your basic knowledge about powers and properties, which we actually cover in the future, but just for now, we have a property that if we have a to the power of m and then to the power of n, if it is nested, m is inside and it's outside, then the result is the product of those numbers, of those powers. So that's what we have here. 3 square and then to the power of 50. These two are the same number. And then you can see that 3 square is what? 9? So it's 9 to the power of 50. Mod h. And here the magic happens, right? Oh, what is 9? Oh, 9 is just 1. So we have 1 to the power of 50. Mod h. And now, can you compute 1 to the power of 50? I hope you can, because it's just 1. So that's it. So it's 1. You should divide this long number. How many digits are there? I don't know. 50 digit number? The result is 1. And again, this is a lot nicer than doing that. And I don't think your favorite calculator will give you this long number. But that's how we can use the knowledge of the modulo arithmetic to simplify some computations. And that's the end of the introduction to modulo. There are more to learn. I'm happy to teach, but again, this is just an introduction course. So yeah, let's try to apply our knowledge on this exercise. That's the end of the third section.